First, thank you to the Energy Institute in general, to everybody, and thank you all for coming here today. Okay, first I'm going to make a presentation. I think about 45 to 50 minutes. It will the time it take. I appreciate your participation at any moment, so please feel free to ask or say anything you want, okay? I appreciate your participation. It will be welcome at any moment, okay? Okay, so new activity, data centers, okay? Competition with agriculture, of course, yes, okay? We're trying to know more about this, okay? Between major human activities about water consumption appears a new one, okay? Added to evapotranspiration in agriculture appears and added to evaporation for cooling both nuclear and thermal power plants. Now appears data center. So new activity, yes, mainly it's a new activity. It's increasing very much due to mainly to artificial intelligence, okay? New activities related to artificial intelligence. Location about data centers. Okay, location, maybe the key point is availability for water and energy. Okay, and that's occurs in an irrigation district. In an irrigation district, in general, we have at any point we have water supply. For example, we have maybe a channel. Okay, this is the river. This is a channel. Upstream of the channel, there is a dam for getting the water resources for the irrigation, and we have also power. Power for what? For a pumping station. So we have power, we have energy at the irrigation district. We don't have data connectivity, okay? But data connectivity is cheap. Or at least I think data connectivity is cheap. Okay. Please, go ahead. Any question? No? Okay, so data centers can be introduced every time and more in the rural and irrigated areas due to this point, water availability and energy availability. Okay, data centers activity, a lot, okay? Serve information, okay, every time more and more, artificial intelligence, okay, but also TV, okay? Nowadays, all of us see TV on streaming, on demand, okay? Also, there are a lot of activities, all related to artificial intelligence. Some of them, for example, advanced scientific research, okay? I don't know if it is very powerful or not, but at the end, all activities are appearing very close to data centers. At the end, okay, data centers are working at full computational load. Okay, so if
I was scammed, Mom.
Sorry,
Can you mute yourself?
I think we need to mute the audio.
okay, let me see how to do this.
That's gone. Somebody will do it for you. Not you. Leave it now.
Okay.
You're okay. Leave it.
Okay.
Continue.
Okay, but probably you can mute from here. No? But I don't know. Okay, no problem for me. Okay. Okay, so data centers are working all time at full computational load. Okay, that is because, why? Because they are doing some artificial intelligence work. Okay. The performance is measured through several performance index. One is power usage effectiveness, that is all the energy consumed related to the consumed by the IT technology, and the water use energy, that is the water use per unit of energy for IT equipment. Okay, now it's not working, this. Okay, in this lecture, I will try to address 4 points. These 4 points, okay? The first one, again, what's happening with heat transfer into the atmosphere, okay? And why do we need or is needed a cooling system that evaporates water, okay? How much water is evaporated from the cooling system? We are going to try to estimate those parameters, the water use effectiveness and the power use effectiveness. And also, we are trying to understand if can be some interaction between the fluxes from the evaporation from cooling towers and the evapotranspiration from irrigated crops. At the end, both activities do the same, transfer heat into the atmosphere, okay? And do that through water vapor fluxes. Okay, first of all, we can do this to an artificial intelligence computer program. For example, I put this from Cloud and Tropic, and we can make this prompt. Okay, please say what is water use effectiveness and power use effectiveness as a function of relative high humidity, atmospheric pressure, and temperature. Okay, and temperature. And okay, the artificial intelligence gives a solution, a response, okay? It's a solution, it's a regression solution, linear regression solution, in which power use effectiveness, water use effectiveness are expressed as a function, linear function of temperature, pressure, atmospheric pressure, and relative humidity. Okay, we have a solution. Okay, but this solution is based on what? Okay, it's based on data from official bodies, from literature review, but also in some analytic research, okay? And I put this because some people is doing the same that I'm doing here since many years ago, okay? But maybe with other kind of data centers, okay? Simple data center where when artificial intelligence haven't appeared yet. Okay, how is the data center? How is cooling a data center? Okay, when I'm showing here, okay, let me answer here a progress about cooling in data centers. About year 2005, when we were at Purdue, okay, about that year, cooling data center was made we are climated in this building. Okay, the air is flowing through everywhere. Okay, and the computers are putting the heat into the air. Okay, the air is circulating. In one moment, there were two parts isolated: a hot part and a cold part separated. Then there was some improvement, probably around 10 years later, in which cooling was water, evaporative cooling was introducing for cooling the data centers. Okay, and more recent advances are related to take the heat just where it is generated. It is generated just at the chip level. Okay, the chip level is composed by tiny condenser, resistors, and transistor. Very, very tiny. Okay, every time that a transistor change its states, some heat, there is an energy needed to shift the state of the transistor. And those tiny transistors in a chip produces the heat. So the heat has to be removed from the chip level to the ambient. Okay. Another improvement was just take the heat just at the very small chip level. Okay. Some progression. Okay, all the progress reflects increasing energy efficiency and thermal control constraints. Okay, just to improve the cooling systems. At the end, all the heat has to be transferred into the atmosphere or a water mass. Okay, can be the sea, a lake, groundwater. Okay, but at the end, the heat from the chip level has to be transferred to a heat reservoir. Okay, heat reservoir in thermodynamics is a place where we can put or take heat, but temperature doesn't change. Okay. Okay, probably because of transfer can be flows only from hot places to cold places, probably we have to put some machines in the middle. Okay, machine for increased temperature. For example, we cannot. We are going to see in the next slide. So, okay, bear in mind that probably we have to put some machine in the middle or transfer the heat directly. Okay, the machine in the middle is just for increase the temperature of the flow, because the heat can only be transferred from a warmer point, from a hot point to a cold point. Okay, it's the second law of thermodynamics. Okay, and also we can be in mind that data center can be included in the circular economy. Okay, we can use this heat from heating other activities. Okay, from water treatment plants to buildings, in houses, whatever. Of course, we can use low quality heat or high quality heat. High quality heat is heat of high temperature. So we can use also increase the temperature of the refrigerant fluid to get high quality heat by, for example, a heat pump. Of course, heat pump needs more energy. But circular economy is thinking about doing this. Okay, how works a data center? Okay, try to focus on an example, a concrete example. Okay, we have a data center. A data center has chips. The chips are grouped into racks. And okay, the temperature of these elements must be between temperature range according to ASRAE, okay, American Society of Heat, Refrigerating and Air Conditioner Engineers, must be around 18 to 27 Celsius degrees, more or less. Okay, what to do with how to transfer 27 degrees to the atmosphere? Okay, we need how to do this. Okay, for doing this, probably if we have low temperature, we can do that direct. Okay, direct cooling. Okay, transfer direct. But what happens if we have a temperature like 25 degrees, 30 degrees? Okay, we cannot do that. We have to increase temperature. Okay, so for transfer heat into the atmosphere through evaporation, that is a method that uses water but requires low energy. Okay, we need to increase the temperature of the water. At the end, we have an evaporative cooling tower that is working as a standard way, introducing water temperature at around 50 Celsius degrees, is getting cool water about 15 Celsius degrees. Okay, and for doing that is consuming water. Okay, the water liquid that is going to be evaporated and is consuming some energy. Okay, the rest of the energy comes from the IT power and also from the machine that increases the temperature from the low temperature source, the low temperature point to the high temperature point. It is called a chiller. Okay, so at the end, this is the flux of energy and water. Okay, we have a flux of water at the cooling tower. Okay, water is evaporated. We have a flux of energy, energy for the IT power, energy for the chiller, energy for the cooling tower, okay, to move the air, okay. And I put some standard size of a data center. A data center nowadays, has this standard, 2.5 megawatts of IT power per 1,000 square meters. Okay, more or less that is a standard. Okay, so for bearing in mind, okay, what size and what power are we talking about?
One question here: how do you account for gradient difference? Temperature gradient here is on the data center side. It's like 9 degrees Celsius, right? Yeah. 18 to 27. The other one is very large, almost 35 degrees Celsius.
Okay, these machines can do that. Okay, there are vapor compression cycles are able to do that.
Of course, there is additional energy that's going here.
Yeah, additional energy. Of course, transferring heat from a cold temperature point to a higher temperature point needs energy. That's this energy.
It's different than typical heat exchanger.
Okay, well, I'm going to talk a little bit about heat exchangers. Okay, but of course, this is a machine, and this machine can do this. Okay, probably there are several stages, several steps. Okay, and using several stages and several steps, this can be done. Okay. Thank you for your question.
So this is not a typical chiller, that the one we use in other sectors. This is especially designed.
No, I think it's a chiller used in many sectors. I think it's a typical one. But okay, I'm not an expert in chillers. I'm an expert in irrigated engineering, agricultural engineering. But I think this machine is a standard one. Okay, it's not very, very special. Okay, probably we have several. It's a machine, but with a couple cycles inside. Okay, maybe okay, one here, okay, and several stages. Okay, thermodynamic engineers can do this. Okay, okay, let's go. Okay, I'm going to present an example. Okay, in which I'm going to study what happened in a cooling tower, in an open cooling tower. Okay, I'm going to study the operation. In a cooling open tower, okay, we said that when we are going to get cold water at about 15 degrees, okay, we are going to send to the data center. We are going to receive hot water from the data center after the chiller at about 50 degrees. Okay, this water has to be sprayed inside the cooling tower. This water has to be infiltrated into a film material. Film material is a porous media where the heat interchain are going to occur, this film material. And on the other side, there is a air flux. There is a air flux in and air flux out. Air flux out is warmer and moisture, and high with warmer and with higher moisture. Okay, so okay, I'm going to explore. Okay, what happens if I consider 15 degrees and a standard, 50 degrees and a standard? Of course, this we are going to see that this temperature, if we increase this temperature, the effectiveness of the system increases also. Okay, but the standard materials, okay, the standard materials only support 50 degrees. If we want to get more than 50 degrees, we have to change. We have to look for other material different to the standard material. Okay, the standard materials are made for supporting for not degrading below 50 degrees. Okay, but over 50 degrees, the materials can be degraded. Okay, so okay, I didn't talk about makeup water. Makeup water is the water that has to be filled because of evaporation. It's the water to compensate evaporative losses. Okay, how to do this? Okay, what do we want? We want to calculate water consumption, energy consumption. Okay, the water consumption is because of evaporation, and energy consumption is because of the mechanical consumption at the fan. Okay, all this air has to be moved. How to avoid this? Okay, with the principles: mass conservation for water, for dry air, energy conservation, okay, at this circuit, also at this circuit, okay. And also, we have to take into account the second law of thermodynamics, entropy, okay. Variation of entropy must be positive, okay. So we're going to consider this. Equations, okay, equations. Okay, equation of property. First of all, pressure, atmospheric pressure, okay, 0.1 megapascal. Atmospheric pressure, okay. So atmospheric pressure, constant pressure, we have that thermodynamic properties, enthalpy, H, and specific enthalpy and specific entropy are function only of temperature. Okay, they are tabulated. Okay, tabulated, of course, we can make a regression. Okay, it's better for using computers. Okay, if we are going to work with this, because you can ask to me, okay, how did you do that? But also I made regressions, okay, for the properties. We have some relation about psychrometry. Okay, psychrometry is the science that relates water, humidity, and air. We have the mass conservation equations. Okay, flow rate relates to heat coming from the heat rate coming from the IT equipment, and the mass flow rate coming from the makeup water, the water needed for filling, yields to the water use effectiveness. Okay, we have also the energy equation. We can calculate in a straightforward the mass flow rate for the dry air, and we can calculate the entropy variation. Okay, entropy variation, we have some physical limits. Okay, we have only to consider that the solution has to be. We can consider only the solutions with positive variation of entropy. Okay, at the end. Okay, sorry. What are the input variables? The input variables are temperatures, 1, 2, 3, and 4. Temperatures, the power, IT power, and are also input variables, a mesh grid made with a range for temperature at 0.5 and relative humidity at 0.5. Okay, so for a mesh grid, we can calculate a chart. Okay, the mesh grid is the y-axis for the relative humidity and the x-axis for the temperature. So at the end, we have this chart. This line is the boundary, okay? Zero variation of entropy, okay? So the solution at the right-hand side cannot be possible, okay? Only the solution at left-hand side. There is other boundary here that is condensation, okay? So below our line of condensation, we cannot work. Okay, the cooling tower cannot operate. And we have the results. We have the solid lines represents the water use effectiveness. That is the consumed water. And we have a consumed water from 1.5 liters per kilowatt, 1.5, 1.2 to 1.45. Okay, and we also have the max flow of air, humid air, that the fan has to move, okay, that needs power, mechanical power, okay? So we need less, to move less mass flow rate here from 60 kilograms per kilowatt hour, from 60 to 240, okay? So if you observe, we can make an optimization, okay? If we try to reduce the water use, we have to move from this line to this line, or from this line to others, to the right-hand side. But also, we have to reduce, if we do that, for getting the same result, we can reduce the mass flow rate. Okay, where do operate cooling towers? Cooling towers, as a standard, operates at the point where it needs the less amount of energy. The least amount of energy is this line, okay? This line, where they have to move the less flow rate, the lesser flow rate, okay? I put a positive variation of entropy, okay? Not zero, some realistic, but invented, okay? I don't know what is variation of entropy, okay? I don't know how is isolated the cooling tower, okay? But I consider that, okay, maybe the cooling tower can work with some positive variation of entropy, and this point is the standard point for working, okay? Near to 100% of relative humidity and consuming the less energy as it can, okay? But what happens if we try to reduce, for example, the energy? We have to increase, if we try to reduce the water consumption, we have to increase the energy consumption. So, okay, we can study 3 points, for example. Okay, taking into account that this point needs different energy and different water consumption. Okay, if we analyze them, we have a water consumption from 1.32, this one, 1.24, and 1.15. And the mix, okay, the mix is given there, 60, 160 kilograms of humid air per kilowatt of IT power, okay? We can consider that the mechanical energy is related to the flow rate. We call head losses, okay? Head losses due to friction. Okay, but if we consider head losses of pressure difference to be compensated by the fan, if we compensated that head losses are proportional to the square of mass flow rate, we can calculate what is the power needed per unit of IT power. Okay, and we can get a relation between the water and the energy. Okay, and then we are going to introduce the water nexus. Okay, in the water nexus, there are trade-offs between water and energy. Okay, so to introduce this, I'm going to study one example, one case. Consider that we have an infinite source of water, the sea. Okay, the sea is salty water, and the salty water has negative potential. Okay, remove the salt, forgetting fresh water. We need to put some energy. This potential, 25 minus 25 bars, are equal to 0.82 kilowatts per cubic meter. And if we shift to the inverse, we get that, okay, if we put 1 kilowatt, we can get 1,200 liters. Okay, if we consider the desalination efficiency of 0.3, is quite realistic. Okay, 0.3, from 1 kilowatt, we can get 370 liters. Okay, where are 370 liters per kilowatt hour? Okay, is armor between these 2 points, between this and this. Okay, so if we consider seawater, our optimum will be around here, between this point and this point. Okay, of course, if we have infinite fresh water, our optimum point is this. Okay, but this infinite, but fresh water is not infinite never. Okay. Okay, let's study about cooling towers. Okay, performance of cooling tower. We can study, for example, what happened with temperature of water. Instead of putting 15 degrees, what happened if we put 10? Okay, to compensate, maybe the question, okay, maybe the question to compensate the difference, okay, and try to compensate that difference. Okay, we can get that, of course, we can obtain the share, and we know that if we put 15, for example, at this point, the point optimum for infinite fresh water, we can get 1.32 liters per kilowatt hour, while in this case, we could get 1.35. Okay, so we can reduce the temperature of water for cooling the data center, but we are going to increase water consumption. Okay, we're going to study what happened with temperature of air, the incoming air in the tower. For example, one day, at the moment in which temperature of the air is 25 degrees, and what happen if we have 30 degrees? Okay, if we change the temperature, of course, if we change temperature, also change the relative humidity. Okay, there's several variables, but in any case, if we have more temperature, we increase also both in this chart and this chart. We are going to see that we are going to increase the water consumption. Okay, so if temperature instead of 25, like here, we introduce water to 30 and 30, I reduce the relative humidity. Okay, so okay, there are many possibilities. Okay, we can change temperature of the air, maintaining the relative humidity, but probably that's not make sense. Okay, who knows? We have a lot of possibilities to explore. Okay, but in any case, okay, I'm going to explore now the question about the 50 degrees. Okay, the question about the standard. Okay, we can compare what happens if we introduce 50 degrees compared to 45 or to 55. Okay, 55 is over the standard. Okay, if we reduce the temperature, for example, from 50 to 45, we are going to get also, we are going to need more water per unit of energy. Okay, we consider this line. and okay, from 1.32 to 1.35, a little bit. Okay, but if we increase the temperature, we are going to need less water. Okay, so for reducing the water necessities of the cooling tower, the best strategy is to increase the water at the entry of the hot water at the cooling tower. Okay, but we have a limit. The limit is the standard fill of the cooling tower.
One question here: what is the fundamental, thermodynamic consideration that increasing temperatures are favorable? Is it the dew point? At higher temperatures, we have a higher dew point so that we can absorb more water?
Dew points are this region. I could draw a line that is dew. Okay, in this region there is no dew, no condensation. Okay, theoretical condensation. Okay, of course. Then the process is not perfect. Okay, and condensation can occur, but thermodynamically and theoretically, the condensation occurs below this region where there is no lines and no charge.
But this recommendation will change the design of the cooling tower, the material used, correct?
Yes, I read that sometimes there are cooling towers that are constructed using filling materials or material for the filling different to this one, and temperature can increase even to 70 degrees. Okay, but
it also changes the dynamics within the data center because the chips now has to operate at a higher temperature.
I think no, because they are independent due to the chiller. Okay, the chiller makes independent both circuits.
Okay. So it decouples actually both systems, the chiller.
Yeah, the chiller decouples are independent.
If you are increasing the temperature, chiller design becomes more complex, but what happens to the energy that you are going to put into chiller? If the temperature is increasing, it doesn't mean that you are going to need more energy in chiller.
Okay, maybe. Okay, that must be addressed. Okay, but at the end,
I mean, more energy per batch.
Yes.
But you have to look into the total energy.
Okay, of course.
Maybe not.
Of course.
The energy per batch will change, but not the total energy per.
Okay, I agree with you, but probably a chiller is only a machine. I think we have to think in a chiller in a different way that we think a refrigerator does. Okay, a refrigerator at home takes hot from the inside of the refrigerator and puts directly into the atmosphere. Okay, but the chiller takes heat from the data center and puts into the cooling tower circuit. Okay, don't push it directly to the atmosphere.
Yeah.
So it depends also. Are you conserving energy or conserving water?
Yeah, there is a compromise, or there is a trade-off.
Yeah. Okay. I didn't study chiller. Okay, it can be done. Okay, but I'm going to present only the cooling tower. Okay.
Yeah. Because if you go higher temperature, you have to remove more energy from the water, right?
Okay, let me. Okay, it has to be calculated. Maybe the chiller only transfer power from the data center to the cooling tower. Okay, if we consider that if we avoid temperature, okay, temperature is only a state. Of course, it's related to the quality of the heat. Okay, but if we consider that the chiller only makes only a transmission of heat from a cold point to a hot point. Okay, of course, for transmitting 1 kilowatt, the chiller needs an additional amount of energy. Okay, but okay, I didn't study. It must be addressed. Okay. Thank you for your question in any case. Okay, the heat exchanger. Heat exchanger, okay, good for winter, cold conditions. Okay, we put hot water and we get water that increases temperature. Okay, the water at the outside, for example, for the tower, okay, must be below the water coming from the data center. Okay, this can be the temperature from the data center. Okay, this temperature goes to the data center again at less temperature. Okay, this water goes to the cooling tower, and this water comes from the cooling tower. We can put a heat exchanger, okay, and the question is that we are going to get always less temperature going to the cooling tower that the temperature coming from the data center. Okay, that's a heat exchanger. Okay, the spontaneous transmission of heat. Okay, if we consider the charts, okay, we can have a trouble. Okay, we have a very narrow region in the chart. Okay, cooling tower cannot operate. Okay, so if we don't have a really okay, if we cannot increase temperature until 50 degrees, more or less, we are going to get good results for cooling towers. But technology solved that in some way, creating the mix cooling tower, the closed loop cooling tower. Okay, now the water from the data centers comes hot and okay, reduces its temperature and goes and come back to the data center cold. Right? Okay, it's called by evaporation. Now evaporation is a closed circuit. Okay, we have a pump spraying water. The water comes here again. Okay, and the water inside the cooling tower doesn't mix with the circuit of the other cooling tower. We have two possibilities now. Stop the pump. Okay, so the heat is going directly through convection directly into the atmosphere. Good for winter days or cold days. If we are in warm days, we have to spray water over the pipes. Okay, the pipes is going to evaporate, and the latent heat is going to take heat. Okay, the fundamentals of the closed loop cooling tower are the same that the open tower. Okay, the fundamentals, but a closed loop cooling tower can work putting the heat directly into the atmosphere. Okay, that is possible in winter days. Okay, of course, it has other advantages. For example, this water gets dirt, mud. Okay, so okay, we are not going to put this water inside this circuit. Okay, so for clean operation is better. Okay, for summer we need the chiller. Okay, the chiller only do this, makes possible this change to get to put this amount of heat and transfer this amount of heat here using a vapor compression cycle. Okay, I didn't address in this study. Okay, but I think it makes sense to do this. Okay, sorry. Okay, so heat transfer through mechanical vapor compression cycle in a chiller. Okay, of course, chiller has a coefficient of performance. Coefficient of performance is not effectiveness. Is not the performance coefficient. No, okay, it's not the relation between energy use per unit of energy consumed by the chiller per unit of heat transfer. Okay, it's other coefficient, but we can get from this coefficient, we can get that relation. Okay, now, okay, we are shift to the evapotranspiration. Okay. Any question at this moment? Okay. Okay, so evapotranspiration. We can address evapotranspiration, assuming two scenarios: no interaction between evaporation fluxes from the crop and evaporation fluxes from the cooling data center, or they interact. Okay, water vapor data fluxes coming from the cooling tower increases the relative humidity of the air, so at the end it affects the evapotranspiration. Okay, some basic knowledge about that. First of all, okay, vapor coming from a cooling tower has to be spread into the atmosphere by two mechanisms: advection and diffusion. Okay, so we have two principles. Same that water vapor fluxes coming from a crop. Okay, same mechanism: advection and diffusion. Okay, for study the advection diffusion, advection and diffusion from a cooling tower, we can study, okay, at any position, we can study the concentration of the contaminant. Okay, contaminant for us is the amount of water, the vapor water. Okay, the amount of vapor water is the concentration. So we can study the concentration of vapor water. At the end, the concentration of vapor water is relative is the humidity of the air. Okay, we have an equation, a partial equation in which we have variation of concentration in time. We have the advective term. Okay, so the concentration moves according to velocity. Okay, the wind velocity moves the vapor of water. We also have a dispersion or diffusion due to turbulence. Okay, and of course we have to take into account a source. Okay, a source or a sink for the equation, but for us it's a source. Okay, so we have for this model that can be quite complex for solving. Usually only numerically is possible. We have a steady state solution, quite simple, very easy to implement in a computer program. Straight. So if we use the Gaussian plume model, valid for a steady state, in which if we consider that the wind is in the x direction, we can get directly the concentration of a contaminant. In this case, a vapor of water. And vapor of water, of course, is a long equation, but simple equation. Okay, it's straight. We can at any point x, y, zeta, we can get concentration. Okay, in a direct way. Of course, in this equation, first approximation. Okay, I didn't consider the convection effect. Okay, the moisture is less dense than dry air, so there is a convective effect. Okay, I didn't take into account. It is possible. It's possible, but the first approach I didn't take into account. Okay, second approach. Okay, the plume center line, this height is equal. Okay, consider is equal to the cooling tower height. Equal. Okay. That depends on the velocity of the fluid. Okay, the vertical velocity of the fan. Okay, the flux rate makes that the plume center line gets higher than the height of the tower. I consider the same. Okay, and also this is a key parameter: eddy diffusivity, turbulence. Okay, I consider a standard coefficient constant is not constant. Okay, the eddy diffusivity is the key parameter. Okay, but we consider an standard one, just a first approach. Okay, if we want to get inside eddy diffusivity, we have to study in detail planetary boundary layer, a concept about fluid mechanics. Okay, okay, with this approximation, we are going to join with our cooling tower. Okay, our cooling tower is 25 degrees, 30% of air humidity. We put water at 50 degrees, and we get a flow rate mass of 1.32 kilograms per hour per kilowatt. Okay, if we consider a standard data center, we get that we are going to put into the atmosphere 0.92 kilograms per second. Okay, I said, okay, that's a lot. That's a lot. This is bigger than we need for irrigate 1 hectare 1 day in July. Okay. Bigger for about approximately 0.7 kilograms per second are needed for irrigate 1 hectare per day in July. Okay, so I thought, okay, that's a lot. Okay, so it makes sense that it can interact. Okay, let's go to calculate the plume. Okay, the Gaussian plume. If we calculate the Gaussian plume, it represented a concentration at 2 meters elevation over the ground. 2 meters because evapotranspiration data for temperature, for wind are measured at 2 meters. So I'm going to compare. 2 meters is the standard for agrometeorology. Okay, this is the concentration. Okay, so I said, okay, of course, concentration is higher close to the cooling tower, and the concentration, of course, is much lesser far from the center. Okay, I consider this concentration line, the concentration line for water vapor of 100 grams per liter. This concentration reaches only this scale to this scale less than 50 meters. Okay. Okay, so close to the tower at only 50 meters of the cooling tower, we get about a concentration of vapor of 100 grams per liter. From this temperature and relative humidity change and only increases from 30 to 30.4%. Okay. Relative change is only 1%. Okay, 1.5% only. Okay, in a region not far than 50 meters. Okay, and far from 50 meters. Okay, think never. Okay, is insignificant. Okay, okay. What happens if we put this concentration on evapotranspiration? Okay. Evapotranspiration, okay, I'm going to go a little bit faster, okay? Evapotranspiration, of course, is the activity of the plants, of the crops, okay? The crops needs, for making photosynthesis, need radiation. So we have now in the evapotranspiration process, we have radiation as a new variable, is the source for energy for the crops. Radiation, okay, for radiation, the crops in the leaves makes photosynthesis. Photosynthesis is the way to convert inorganic CO2 from organic carbon. Okay, and what happened with water? Okay, water, the molecule of water has the same size, that approximately the same size that CO2, and when the gas interchange is made through the leaves, through the stomach, okay, the water flows out of the leaves. Okay, that's evapotranspiration. Okay, evapotranspiration cannot reduce without reducing productivity of the crop. Okay, so we need. How do we study evapotranspiration. Okay, we have evapotranspiration with the same equations, mass conservation, energy conservation, same concepts, but in a different way. And we study through a standard hypothetical reference crop. Okay, the standard reference crop has 3 values. One is albedo. Okay, there are 5 minutes. Okay, thank you. I think no more. Okay, albedo 0.23, aerodynamic resistance of the crop, and also surface resistance. Okay, and the fourth, 12 centimeters. Okay, this is a reference. Okay, this crop is similar to a grass, well irrigated. It's only a reference for making calculation. Okay, it's like a grass crop. Okay, what happened in a normal day? Okay, this is the climate data from a weather station, temperature, dew point. Okay, difference gives us the relative humidity. We have wind. The points are the gust of wind. Okay, wind direction and radiation. Okay, what happened? Okay, but what happened is that with all these parameters, okay, this is not needed. Okay, with radiation, wind velocity, temperature, and relative humidity, we can calculate evapotranspiration. And the result is, okay, if we increase 1% the relative humidity, okay, if we increase in 1%, evapotranspiration is only reduced less than 0.2%. Okay, no reduction, insignificant reduction. So the effect of a cooling tower in a irrigated region is negligible. Okay, we can study cooling towers and evapotranspiration independent, as in, okay? That's a conclusion. Okay, and it's almost all. For illustration, I put this curve, I superpose to the radiation curve, trying to illustrate how is evapotranspiration. When wind increases, like happens at the right-hand side of this dust line, the evapotranspiration, the blue line, separates from the radiation line. And if wind is not very high, okay, both lines are almost the same. At night, it happens the same. Okay, if wind increases, evapotranspiration separates from the radiation line. Okay, that is only for to show that evapotranspiration is made of radiation balance and advective balance. Okay, both elements are included into the equation. Okay, and okay, my conclusions. Okay, we make this evaporative cooling and evapotranspiration to process to transfer heat into the atmosphere. Okay, water effectiveness, power effectiveness are a function of temperature and relative humidity. Okay, we can get the optimum relation between both according to the water energy trade-offs. For example, the example of the salty water. Okay, this energy from the sea. Okay, evaporation from a data center effect is insignificant in evapotranspiration. Okay, it's not important. Okay, so we can consider data center and irrigated agriculture as independent. And my opinion, okay, until data centers would not be introduced into circular economy, water competition will increase, okay, because data centers are increased, okay, and even more and more artificial intelligence is used in our lives, okay. Much time we don't know about, okay, we don't know that we are we are using artificial intelligence, but artificial intelligence is used. And okay, maybe a productivity index for data center is needed. Okay, I don't know any productivity index for data center. Okay, I don't know if any one of you knows productivity index. I don't know. Okay, and that's all. Thank you very much.
Thank you.